All right, let's get right into it. Today we're tackling one of the most important ideas in magnetism, something you see all over the place but maybe don't fully get, the sinθ family of formulas. We're going to figure out the big secret behind why, in physics, perpendicular almost always means you're getting the maximum effect.
So let's start with a question. It seems pretty simple on the surface, but it holds the key to everything we're talking about today.
I mean, think about it for a second. It just makes sense, right? If the wind is blowing parallel to the sail, it just kind of slips right by, and the boat doesn't really go anywhere. But when that sail catches the wind at a perfect right angle, whoosh, that's when you get the biggest push. So what's actually going on here? Why does being perpendicular create the maximum effect?
Well, it's pretty straightforward. When the interaction is parallel, so the angle is 0, there's basically no effective force. The wind just skims on by. But when that interaction is perpendicular, at 90 degrees, the sail catches everything. That's the moment of maximum impact. And here's the really cool part. This isn't just about sailboats. This is a universal principle in physics. It's the exact same reason why a wire carrying electricity feels a force in a magnetic field. See, in physics, forces often get broken down into components. And in these cases, the universe only really cares about the part that's perpendicular. So, let's prove it.
Okay, so let's make this official. Let's translate our sailboat idea directly into the language of physics and electromagnetism.
Here's the one-to-one matchup. The wind, well, that's like our magnetic field, B. The sail, that's our wire carrying a current. The angle, theta, is of course the angle between the wire and the field. And guess what? Just like the sailboat, we get the absolute maximum force at 90 degrees and absolutely zero force when they're parallel.
And this brings us to a classic exam question, a total trap that gets so many people. The question seems simple enough. You've got a wire running parallel to a magnetic field. Find the force. Your first instinct is probably to grab your calculator and start plugging numbers into a formula. But hold on, this is where the mistake happens. So many students just jump right into F equals BIL, totally forgetting about the angle. The key word here is parallel. If the wire is parallel to the field, the angle, theta, is 0 degrees. And what's the sign of 0? It's 0, so the whole force is 0. The wind just slips by the sail. It's a trick question. So if you remember one thing, make it this. It's a great little mental shortcut. Max when perpendicular, 0 when parallel, sine tells all. Say it again. Max when perpendicular, 0 when parallel, sine tells all. That simple phrase can save you a ton of headaches. Okay, so we know sine theta is a huge deal. But where does this formula, F equals BIL sine theta, actually come from? Let's dig in and find out its origin story.
It all starts with something really small, a single charge, Q, zipping through a magnetic field. That charge feels something called the Lorentz force. Now, let's scale that up. A wire is just a whole bunch of charges moving together, right? So we figure out the total charge in the wire. Then we connect that to the current, I, which is really just about how fast those charges are drifting. When we put all those pieces together, we get a formula for the total force on the wire, F equals ILB. But wait, that formula only works if everything is perfectly perpendicular. To make it work for any angle, we have to isolate just the part of the motion that's perpendicular to the field. And how do we do that? You guessed it. That's where our friend sine theta comes in.
And there you have it. F equals BIL sine theta. See, it's not just some random formula you have to memorize. It's built up step by step from the most basic physics of a single moving charge. And hey, if you need an easy way to remember this one, just think of the word film. Force, I length, maximum perpendicular. Film. It's got all the key ingredients right there. Okay, so we've mastered linear force. Now let's pivot. Literally, what happens when this force doesn't just push something in a straight line, but makes it spin? To get our heads around this, let's use a new analogy to understand torque. A revolving door is the perfect example of torque in the real world. You already know this. To get it moving easily, where do you push? You push perpendicularly to the hinge as far out as you can. That gives you maximum torque. Now, what happens if you try to push right on the edge of the door parallel to the hinge? Nothing. You get 0 torque. Do you see the pattern here? It is the exact same principle as the sailboat and the wire. It's all about that perpendicular interaction, and sine theta is the perfect way to describe it. And this right here, this is the big aha moment. The force on a straight wire, F equals BIL sine theta, actually evolves. When you bend that wire into a loop, that straight line force transforms into a rotational force, a torque.
And it's described by a very similar-looking formula. They are part of the same family, and they both use sine theta because they're both measuring the exact same thing, perpendicular effectiveness.
So how exactly does the force on a wire magically become the torque on a loop? Let's crack the code and derive the second big formula in our sine theta family. Let's break it down. Picture a rectangular loop of wire in a magnetic field. Now, two of the sides are going to feel a force. What's interesting is that these two forces are equal, but they're pushing in opposite directions. This pair of forces is called a couple, and its whole job is to create a turning effect. Now, the torque for a single loop is just that force multiplied by the lever arm, which, after a little math, simplifies down to IAB, where A is the area of the loop. But what if the loop is tilted at an angle? Well, that effective lever arm gets shorter. It actually shrinks by a factor of sine theta. And finally, if you've got a whole coil with, say, n turns of wire, each turn adds to the torque. So we just multiply the whole thing by n. And that brings us to our final result. The torque on a current loop is NIAB sine theta. You see how it flows directly from the force formula we already figured out? They're totally connected.
And for this one, we've got another great mnemonic. Just remember the name TINA. Torque, INA, angle sine. TINA. It helps keep all the parts of the formula straight in your head. Now for the most important part. Why does really understanding this connection, this whole formula family, actually matter? Well, let's look at the payoff in a real exam situation. This table really shows the difference. On one hand, you have the student who just memorized the formulas. They see them as two separate things. They might solve part A about the force on a wire, but then part B asks them to turn that wire into a loop and find the torque, and they're stuck. But the student who understands the concept, they see the family connection. They know force becomes torque. For them, solving both parts is fast and easy.
So, what's your final exam strategy? First, and I cannot stress this enough, always check the angle first. If things are parallel, the angle is 0, and the answer is probably 0. You might not even need your calculator. Remember that force and torque are just two sides of the same coin. When a wire becomes a loop, force becomes torque. It's the same idea. Understanding that connection isn't just about getting a better grade, it's about seeing the elegant, unified way that physics actually works.